Fine. So, in our last class, we had completed our quantization, our first round quantization in some light cone gauge, okay, of the string. So, light cone gauge, because what we did, if you think about it, is identify light cone time in space-time with light cone time on the world sheet of the string up to a normalization constant. Okay, because we said that x plus was sigma plus. Well, actually, no, I just said that wrong. A light cone time in space-time with actual time on the world sheet of the string. Yeah, because we said x plus was something times tau. The fact that we chose a light cone direction in space-time gives it this name, light cone gauge. Okay, we're now going to, this was great for understanding the motion of a free string. But in order to study string interactions, using a gauge that molds the Lorentz invariants, and it is somehow not very nice, is a significant disadvantage. Okay, so we're going to get more serious and study the quantization of string theory in a more symmetrical gauge. Okay, we're going, the kind of, roughly speaking, the kind of thing we did is very similar to what we did when we studied the particle right at the beginning. We studied the particle as number go to action, and then just used as many degrees of freedom as there really were in the theory. Identified one of the coordinates in space-time as time. As the time on the world sheet. We're doing something similar here. We identified one of the coordinates in space-time as time on the world sheet. But here, the constraints allowed us to eliminate, throw away another coordinate as well. Right? We identified x plus as tau. We could throw away x minus, all except 0 1. And we were left only with the 24 physical transverse oscillations. 24 because the total number of dimensions we decided was 26. Okay? And that's very nice, but clearly there's something odd about having 24 excitations in a 26 dimension space. So what we're going to try to do is to do something more like our final covariant quantization, where at every stage we've maintained Lorentz invariance, and things will turn out more elegantly. We'll see things more elegantly, more structurally. Okay? In order to do that, we're going to need to understand what's a technical subject called conformal field theory. Okay? So the next 2 or 3 lectures will just be about two-dimensional conformal field theories. Okay? I'll motivate that in a moment. But before going on to that motivation, before going on to a technical study, just a few words about where we're going. You see, when studying particles, the first quantized formalism, the formalism we talked about in our first lecture, can actually be used to generate all Feynman diagrams of quantum field theory. Okay? This is not how quantum field theory is normally presented. You normally start with a space-time Lagrangian and work up Feynman diagrams from there. But you can equally obtain it from what's called the world line approach. Okay? Where a Feynman diagram like this really represents the propagation of a particle from point X to point Y, governed by the action we talked about in the first lecture. And then it loops like this. Start with singular events in which now particles propagate like this and join up. So each propagation factor gives you a propagator, and that the usual propagators of quantum field theory come out of the Lagrangian we studied in the first lecture. I'll give you an assignment and a homework sheet, by the way, in which we'll do some particle physics. We'll do some Feynman diagrams using the world line approach. It's fun. Okay? But the point I wanted to make here is that in order to introduce, the action that we talked about gave free propagations. In order to introduce quantum field theory with interactions, we need world lines with singular events. If you think of this Feynman diagram, it's much like Feynman, really as the path of a particle, then there is locally a special point here that's very different from this local point. Because at this point, the path is not a one-dimensional manifold. It's not like a little neighborhood of origin. At every other point it is. Okay. Because this point here is special, we need new rules for understanding interactions. That is, we need a rule for telling you what factor to put in here. What factor such a splitting is weighted by in the particle. Okay? Just knowing how the particle propagates along a smooth path doesn't tell you the rules for bifurcations. Because it's a new thing. Even locally on the path, on the world line, it's a new event. Okay? And the different rules for how these particles bifurcate are the different interaction terms in this quantitative theory of Lagrange. And as you know very well, different interactions induce very different physics in the theory. So the rule for what interactions are allowed and so on is a very important part of quantum field theory, or the world line formalism describing particles. I've said all this, it's almost obvious, but I've said all this anyway to set the stage with the contrast with what happens with string theory. Let us look at what the analog of this process will be when we deal with strings. Our basic objects are not particles, they're strings. So, you've got this little loop. It's traveling around some path, which I'll try to draw mimicking this path. You look at it from far away, this looks very much like this. But what's the interaction process? The interaction process is something like this. Okay? Now look at this interaction process. The local evolution of the string in any little region of the world sheet is governed by our string world sheet action, the one we've written down. Since this manifold here is smooth, in every region, including the interaction region, a little local part of the string of the world sheet is governed by the same action that we wrote down, just because the world sheet action was local. Okay? So if you know what the rules are for a string to propagate from here to here, and if you demand that it's governed by the same local world sheet action, you also more or less know, there's a few ambiguities we come to this, but you also more or less know what the rules are for the string to split up into two and then join it. Do you understand? Because this is governed just by local physics on the world sheet of the string. This is actually a remarkable fact, which makes string theory a very tight theory. Once you work out the rules for how free strings evolve, the rules for how they interact, up to a few small ambiguities which we'll deal with, are determined. The rule for splitting of strings, rejoining, is not independent of the rule for free propagation. There is no analog of this statement in particle physics, in the theory of particles. And this thing already tells you that the theory of propagating strings is a much tighter theory somehow. It'll be, in ordinary particle physics and the Lagrangian on your t-shirt, you get to choose separately what the masses of the particles are and how they interact. The kinetic and the interaction terms are different. Okay? We don't get to choose these differences in string theory. Okay. So, if we understand how to quantize our world sheet thing, our world sheet Lagrangian, in particle physics that would only give you free quantum field theory. And building blocks of interacting quantum field. In string theory, it gives you all of interacting string theory. Okay? So that Lagrangian is somehow everything. And as we've seen, it's a pretty simple Lagrangian. Okay? Yeah.
How do you include this operator insertion in these cases?
Yeah, we'll discuss this.
Because in this particle wall-line picture, you can do that, like locally.
What?
Means wall-line picture, the picture above, you can do it locally.
Do what locally?
Means insertion part, this operator insertion in this case. Yeah.
You want to do off-shell correlation functions? Is that the point? Yeah. The question of off-shell correlation functions in string theory is complicated. As you know, Ashok is writing papers on it. Let's postpone this. Let's postpone that discussion. Okay. That's, as you know, we've now discovered it can be done, but it's let's leave that now. Okay. Yeah. So.
So how do you represent these interaction, the one loop, two loop terms?
Well, you just have to integrate over all manifolds, including manifold topologies.
So that's where
the topology of the manifold captures the number of loops in quantum field. Okay? But how to do this more precisely is what we're going to do. Okay? So that is the goal of the next 10 lectures or so. And the goal of the next 3 or 4 lectures is to set up the mathematical framework that we will need for this process, and in particular the study of two-dimensional conformal field. Okay? So that's what we're going to embark on now in 5 minutes. But I will first motivate for you why we want to study two-dimensional conformal field. Where does that come from? What is it? Okay, so first let us recall that the action that we were interested in studying was S is equal to 1 by 4 pi alpha prime the whole thing squared, x dot squared minus xi squared. I should actually write, so let me write that. Okay, this was the action that we studied and quantized and had fun playing with. Now, in order to compute scattering amplitudes, people want to do path integrals of this action. So people want to do a path integral of the form dx mu e to the power x. Actually, when we stopped doing this path integral, we also put back the worldsheet metric and do the integral over the worldsheet metric fields also more seriously. But for now, for my present state of motivation, imagine that the worldsheet metric has been fixed away. We're just doing the integral over x. Okay. Now, as many of you know, such path integrals are not very well defined because configurations, for instance, with high energy because they oscillate a lot, are damped out by large phases. Yeah? But phases do damping in a very implicit way because the integrand never vanishes, even for very weird configurations. As many of you know, and how to make this well defined is a bit tricky. Okay? But as many of you know, there is a simple trick to give a better definition of this path integral. That is to define it as an analytic continuation from Euclidean space. For instance, people who are in my quantum field theory course, whenever that was taught, we discussed this in a lot of detail. Okay? So, what we are going to do is to continue our action to Euclidean space and study the path integral in Euclidean space. Okay? Anyone who has questions about what this means, what this analytic continuation means, please come and meet me after class, because this can be a long and slightly fuzzy discussion. Okay? We'll postpone that for. Okay. So, what is the analytic continuation that we want to do? Actually, it's a tricky question. It's a tricky question. Anyway, but what is the analytic continuation we want to do? It's this. We want to turn this into e to the power is. Okay? We want to turn this into e to the power is. I want to turn this e to the power is into e to the power minus s. I want to turn this e to the power is into e to the power minus s. And the way we do that is basically as follows. Okay? The way we do that is basically as follows. The first thing we do is to take this tau and write it as I times tau Euclid. Okay? So let's call this tau Lorentzian. So tau Lorentzian is I times tau. Tau Euclidean with a minus sign. Okay? Okay. So and therefore tau Euclidean is equal to I times tau Lorentzian. Okay? And then just rewrite this action in terms of tau Euclidean. Okay? So what do we do there? Well, firstly we do d tau Lorentzian is equal to minus I times tau Euclidean. And x dot square, which was d by d tau Lorentzian, becomes d tau x by d tau Lorentzian, the whole thing squared, is equal to minus d x by d tau Euclidean, the whole thing squared. Just because I squared is equal to minus I squared is equal to minus. Okay? Now, there's a minus sign here, we get an extra minus sign from here, and then I times minus I is 1. So our path integral becomes e to the power minus s Euclidean of x d of x, okay, where s Euclidean is equal to 1 by 4 pi alpha prime x dot squared plus x prime squared d tau basic, d tau Euclidean basic.
We keep the time in the space time still.
No, actually we will eventually even continue that. Okay, but let me consider you see, since all of these x's are all decoupled from each other, let me for instance consider the path integral for one of the xi's, just so that we separate issues. We will continue that as well. Okay. Now this theory, this path integral here, the path integral generated by this action, okay, is just like a Euclidean. You know, it's got this has SO2 invariance rather than SO1 power 1. It's a Euclidean free boson path integral. Okay? And going to the analog of going to light cone coordinates. Okay? The analog of using light cone coordinates in the Lorentzian theory is to use complex coordinates in this theory. Okay? So let us now try to make sure we follow Pulchinski's conventions. So, what we will do is, okay, now let's call this guy sigma 1 and tau Euclidean is called sigma 2. So, tau Euclidean is equal to sigma 2. Okay? And we will define Z is equal to sigma 1 plus I sigma 2. And Z bar is equal to sigma 1 minus I. Okay? You can see that Z and Z bar go to sigma plus and sigma minus, or sigma minus and sigma plus respectively under the Euclidean interpolation. Okay? So,
here we are allowed to use root 2.
we're allowed to use root 2, but since Pulchinski does not, you know, just because we want to compare with formulas in his book, let us not do that. Okay. Because we'll never know if we're going to use wrong.
Sigma 1 is still periodic, right?
What?
Sigma 1 is still periodic, right?
Sigma 1 is still periodic. Sigma 1 is still periodic. And you see, oh, is sigma 1 periodic? Okay, sigma 1 could be periodic. Okay, good. See, right. See, suppose sigma 1 was periodic. Hang on like 20 minutes. Okay, there's a conformal transformation that takes you from that situation to the one we're studying. Okay, that conformal, let me just say it in words and we'll study it soon. That conformal transformation is the one that takes the cylinder to the plane. Okay? Under this conformal transformation where sigma 1 here, which is periodic, becomes the angle variable of this z thing. Okay, so whether we allow our complex coordinates, our sigma 1 and sigma 2, to live on a circle and r, or whether we allow them to live on r and r, are just related by a conformal transformation. Okay, so we're going to treat sigma 1 as non-periodic. We're going to treat sigma 1 as just extending all through, but that will not inhibit our ability to actually study the case we're interested in where sigma 1 is periodic. Okay? We'll get back to that.
What is it that you're considering now? Are you on a cylinder?
No, at the moment I'm on a plane. I'm on a plane and I will generate the physics of the cylinder whenever I'm interested in it from the physics of the plane.
Yes, so sigma 1 is non-compact.
Yes.
What you're saying is that you have, it represents the x-axis and sigma 2 is the sort of the y-axis. Right?
Yeah, so I'm taking the world sheet of the string.
Yeah.
You know, we had this equation which described local physics, and we could consider that on any manifold. I am for a moment studying this on R times time and analytically continuum. Okay, so this is two-dimensional complex length. Okay, but you might have said that physically we are interested actually in the cylinder. In fact, we'll be interested in many manifolds, but we will in particular be interested in the cylinder. But once I know how to deal with this thing on R2, I will very quickly be able to generate the answers on the cylinder, as we will see. So please go.
Suppose an open string.
Suppose it was an open string. Then we would be interested in some sort of strip like this, which actually can be conformally mapped to the upper half plane.
Okay.
Okay? So again, knowing how to deal with R2 is a great starting point for doing this. All of this we will see as we go. Okay? But for now, we'll just take the simplest example of this manifold, namely R2, and we will see that that will be sufficient for all our, we'll be able to generate all our physics easily from there. Is this clear? Okay. Fine. Okay.
Why periodic sigma 1 is interesting? Why do you want to?
Why? Because closed strings have periodic space. Okay? Right, good. Okay. Now, the next thing we do is to take this guy and just completely rewrite it in Z notation. Okay? Now, so firstly, I'm going to take dz bar. This quantity, what I mean by that quantity, is what I get by doing the variable change. Z is equal to this, Z bar is that, and using the Jacobian formula. Okay? So dz bar is equal to Jacobian, it's equal to the determinant of 1 minus I times d sigma 1 d sigma 2 by the usual variable change formulas. This is just what I mean by dz bar. Okay, which is equal to minus 2I d sigma 1 d sigma 2.
The Jacobian is a determinant.
Mod. This is what I mean by d sigma 1 d sigma 2. Okay? You can word it as you want. Let me go for it. Sorry. That's not You're right. It is. Okay. It's just a matter of notation. There's the measure factor on the plane. When we write dz bar, what do we mean? Okay, this is what we mean. Sorry, right? That's what we mean. Just factor of 2 and just drop the line. Okay, great. Okay. Next, what is this x dot squared times x prime squared in terms of dz and dz? Okay. So what is dz? dz is d sigma 1 by dz times d by d sigma 1 plus d sigma 2 by dz into d by d sigma 2 Okay? Now sigma 1 was equal to z plus z bar by 2, whereas sigma 2 is equal to 1 by I, z plus z minus z bar by 2. Okay? And so dz is equal to half into d sigma 1 d1 plus I d2 minus I d2 minus I d2, and dz bar is equal to half into d1 plus I d2. Okay? The kinetic term, which was d1 squared plus d2 squared, is equal to 4 okay, times dz bar. Okay? And therefore, our Euclidean action, okay, our Euclidean action SE is equal to our Euclidean action is let's see, so where are we? 1 by 4 pi alpha prime times this, which gave us half dz bar by 2, and then del z x, del z bar x into 4. Okay, and therefore we get 1 by 2 pi alpha prime del z x del z bar x. This is what he has. Yeah, good. That's what he has as well. Okay, so we have 1 by 2 pi alpha prime del z x del z bar x. That's our Euclidean action. All this is trivial, it's a matter of rotation. d2z. Okay? It's just a matter of rotation, but okay. Fine. Okay. Now, what we are going to do is to study the path integral. So we take one of these x's, one of the x's which you think of as xi. We're going to study the path integral dx e to the power minus s, where s is given by this action. Minus s Euclidean, where s Euclidean is given by this action. Okay? And we're going to study this action and this path integral and similar path integrals. Okay. We're going to study this action, this path integral and similar path integrals. Now, notice that this action here has a particular symmetry. Under the coordinate change, z goes to f of z. And therefore z bar goes to f bar of z, where f is an arbitrary complex function. This action is invariant because the action is 1 by 2 pi alpha prime dz bar del z of x del z bar of x.
So that goes to f bar of z bar.
F bar of z bar, thank you. Okay, now dz del z x is obviously invariant under the kind of variable change we're making. Similarly, dz bar del z bar of x is invariant under the same coordinate change. So this action is invariant under these combined coordinate changes. This is simply the Euclidean reflection. This is simply the Euclidean reflection of a fact that we had seen earlier in Lorentzian space. What was this fact? that the action had an invariance under sigma plus being redefined as a function of sigma plus, and sigma minus being redefined as a function of sigma minus. You might think that there's a puzzle here. Somebody might think, well, in Lorentzian space, we have two functions worth of invariance. Here we have only one function, because f and f bar are complex conjugates. What's the resolution to this? Because invariance should change. What's the number of parameters should change? What's the resolution?
This function of z and this function of z bar.
Well, it's complex conjugate function of z bar. Z is a complex number. I know people sometimes say you can treat them as independent. That's total nonsense. If you know Z, you know Z bar. Okay. But of course, there is some sense in which that's true. What is that sense? Yes, this is a complex function of Z. So the amount of data in a complex function is twice the amount of data in a real function. Okay? Imagine doing a Taylor series expansion in Z. You have A times Z plus B times Z squared by 2 and so on. A and B are complex numbers. There's two real numbers. Okay? So same amount of invariance as we had in the Lorentzian. Okay? Great. Now, once again, the underlying reason for this invariance is what it was when we studied the theory in Lorentzian space. That is, the theory has, once you couple it to a world sheet metric, has two invariances. The first invariance is diffeomorphism invariance. Okay, any theory coupled to gravity has diffeomorphism. But the second invariance was Weil invariance. So any diffeomorphism whose effect on the metric is a Weil transformation will necessarily be a symmetry of this theory. Because the diffeomorphism undoes, changes the metric, but only after a Weil transformation, which can be undone by Weil invariance. And just as in the Lorentzian theory, the metric dz bar is obviously changed only by a Weil factor, by such coordinate changes. The Weil factor being z f z prime on square. Okay? So I'm just telling you in Euclidean space what we've already seen in Lorentzian space. Okay? That this theory has, at least locally, invariances under analytic changes of coordinates. By what do I mean by invariance? I just mean the Lagrangian is unchanged. If I do this coordinate transformation without changing any metric, the Lagrangian retains its form in the new variables, same form that are in the new variables. Yes?
So this is the residual freedom only, right?
This is the same residual freedom. The same residual freedom, just viewed in Euclidean space. Okay? Now, any theory that has invariances under such coordinate changes, any theory that has invariances under such coordinate changes is called a conformal field theory. Okay? Almost always, conformal field theories always arise for the same reason, that if you coupled to gravity, they were Weil invariant theories. The Weil invariance plus diffeomorphism invariance combined, once you fix the metric to something specific, combined gives you the invariance of invariance under conformal transformations.
Is this only for classical or is it?
We'll study it in great. Okay, what we would mean by conformal field theory is something that retains this invariance, also quantum mechanical. Okay, this theory will turn out to, as we will study.
So, why this is only residual? Looks like a theory.
No, it was residual from the point of view of string theory. So you see, in string theory, what we had was taking this action, coupling to two-dimensional gravity, modding out by diffeomorphisms as well as Weil transformations. So we could use diffeomorphisms and Weil transformations to set the metric to eta. But that did not completely fix gauge invariance. Because any coordinate transformation that up to a diffeomorphism, that retained the form of this metric, any diffeomorphism that retained the form of eta after a Weil transformation would be an unfixed gauge invariance. And these conformal transformations are shown. We've seen, right? That. Okay? So, this was the origin from the point of view of studying string theory. But if we were just studying conformal field theory, we can forget about that. Okay, but this is usually the genesis of why a theory is conformal. If you took it coupled to gravity, it had wide invariance. That's what leads to the conformal invariance on flat space. That's usually how these things work. Okay? This is what we mean by conformal field theory. A two-dimensional field theory that is invariant under these coordinate changes. Okay? That essentially has invariance under wild transformations. Okay? As we're going to see, this is going to be promoted to quantum invariance up to some anomalies, which we will allow. Okay? We're going to dedicate the next 3 classes or so to studying conformal field theories. To start off the study, though, we're going to review some elementary facts about quantum field theory from the viewpoint of the path integral. Okay, the first elementary fact is the question of how an equation of motion. Okay, so we're interested in path integrals like dx e to the power minus st. Okay, much of the discussion for the next half an hour will be general, but you can keep this particular field theory in mind as an example. Okay. Now, you know that classical physics generated by such an action has an equation of motion. We studied the equation of motion to the free Gaussian theory in great detail over the last 3 classes. Now, you know, if equations of motion constrain classical physics, they must also constrain quantum physics. Because quantum physics is not discontinuously different from classical physics. Okay? So the first question you might ask is, what is the consequences, how do we see equations of motion in the quantum theory? Our viewpoint through much of this course will be, for us the quantum theory will be the path integral. So the question we're going to ask is, how do we see equations of motion within the path integral? Okay. So now the first question you should ask is, what are the good observables within a path integral? Okay? That will be of concern to us for most of our course. So what are the good observables? The good observables within the path integral, there could be many, but a class of observables that will be of special interest to us. I need to form my sense of the x times O1, let's call this F1 of x of sigma 1. By sigma 1 I mean sigma mu 1. F2 of x of sigma mu 2 and so on. Local functions of the x's inserted at particular points. Okay? And then expectation value computed under the path integral. Is this clear? These are sometimes called correlation functions.
So just lots of arguments.
Lots of arguments. F1 could be any function you want. For instance, it could be e to the power I k x.
So am I fixing the space-time point of insertion or the worldsheet point of insertion?
No, you're not fixing the worldsheet point of insertion because that you're going to integrate.
Okay.
Sorry, you're not fixing the space-time point of insertion because that you're going to integrate. But you are fixing the worldsheet point of insertion. Okay? This is how we normally do in quantum field. You put some operator at a particular point on your manifold. That's all I'm saying. But what is an operator from the point of view of the path integral? It's some function of the things that you're integrating over. Except that it's a function that is local. You're integrating over x at all the points of space-time. We don't normally consider, we will not be interested in arbitrarily complicated insertions. We're only interested in local insertions. Things that are made up of x at sigma 1, or we could have derivatives, which we will regard as x of sigma 1 minus x at sigma 1 minus delta sigma 1 divided by. Okay? So up to finite number, a derivative could be thought of just a finite number of insertions of strictly local objects.
Just sorry, clarification. The sigma 1, the 1 here inserts the first point.
Yes. So the first operator is inserted at the first point in space. So this is our manifold. Sigma 1 mu, sigma 2 mu, sigma 3 mu are the various insertion points. And at these insertion points you can insert different functions of x at those points. Okay? These insertions functions compute time-ordered corresponding operators in the canonical formulation of quantum field theory. Okay? And these are the quantities that we will be interested in. Instead of writing F, I will usually write O1, O2, O3 to remind you that these are operators. But from the point of view of the path integral, O's are just some function of X. Okay? Is this clear? This is the observable that will be of interest to us for most of our course.
And time ordering has a meaning only in the space of X's.
Time ordering you have to define. So let's suppose that we define time ordering from the Lorentzian theory in tau.
Yeah.
So then that is sigma 2 ordering here.
Also, you're on time ordering on the world sheet itself.
On the world sheet. Yes. So path integral computes time order correlations on the world sheet. This is usual quantum mechanics of quantum field theory. Is this clear? Okay, you all remember why path integrals compute time order correlations, right? Can somebody remind me why that's the case?
Break it up into small pieces.
Exactly. You break it up into small pieces, and those small pieces then are evolution operate, insert, evolution operate, insert. So you're always going in a particular time order. Okay, great. Now, on these observables, we're going to ask what. So suppose now we write this slightly more elegant notation. We'll write this as O1 of x1 mu, O2 of x2 mu, On of xn mu. Understood is that O1 is some function of the fields of x1 and its neighborhood. Okay? Now we're going to ask what is the implication of the equation of
These
motion?
are not arbitrary functions of sigma, right? These are just O1 of x of sigma.
O1 of x of sigma, exactly. So this is bad notation, but it's easier to continuously write. Right, so that's how, the way I wrote it first was the best way. So f, some function of x of sigma 1. Okay, that is abbreviated in usual treatments of quantum field theory by the statement O1 of sigma. Some local operator inserted at point. What I mean by that is some function of the x's at point sigma. Yes, there's no explicit sigma operator.
So why can't you write this x1, which would mean that x,
Which
sigma 1 is x1. I mean, these
X.
are essentially functions of x.
No. There could be x square. Could be even there x. Sigma 1 is a point on the world sheet.
Yeah.
It has nothing to do with these things.
Yeah.
So sigma 1 is whatever it is, but this O1 could be an arbitrary complicated function of x at sigma 1.
Yeah, so what I'm saying is that in the notation, why can't you write x of sigma 1 as x1? These would then be functions on
You want to write O1 of x1.
1.
You could do that. It's just not what's traditionally done. Okay. You see, traditionally operators are labeled by their insertion points. And the fact that they are arbitrary functions of the fields is part of what it means to be an operator. So you just get used to that and then you translate that.
Okay, so maybe I got this wrong. So you mean that x's are not one-to-one functions from the world sheet to the target space or this way?
No, x's are path integrated. So x at sigma 1 can be any value.
Just as being fields. I mean,
they're fields.
Or just as being maps from the world sheet to the space-time.
No, they are.
They are one-to-one.
No, 1 to 1. No, I mean you could have 2 points going to the same x. Is that 1 to 1 important for you?
No, then you could have written the insertions of the world sheet and the insertions in space.
Yeah, but certainly that's not what we want to do. For instance, in vacuum x's, all x's are around 0. Certainly we don't want to get into all that. Okay, no, I mean, no,
Okay, yeah, I understand. You want to say on the world sheet itself?
yeah.
About this time ordering in this Euclidean path integral,
Yes.
it should be time ordering in the sigma 2.
Time ordering in sigma 2 is if you started with time ordering in tau 2, it would be time ordering in sigma 2.
So it's tau in Lorentzian frame.
Exactly. Now, as you will see, different time ordering sometimes give rise to the same Euclidean path integral. The different ways to cut the same Euclidean path. We'll look at this. Okay. Okay, excellent. Okay. This Euclidean path. Okay. So now let's move on to the question of what our equation of motion tells us about. Okay. something like this. We have dx e to the power minus x. Let's take del by del x. Okay? Of e to the power minus s e of x. O1 sigma 1 On sigma n. Okay? And now I'm going to drop the mu as well. Okay? And this is del by del x of sigma, let's say. So I've got an integral. The integration variables are x of sigma for all sigma. And here what I have is the total derivative of an integral. Integral of a total derivative. I've got the integral of a total derivative. Provided boundary terms vanish, which will be guaranteed in Euclidean space because the Euclidean action falls off very rapidly as you go to crazy values of x. Okay? Provided boundary terms vanish, this integral is just 0. Yes?
Not yet, right? We still haven't continued the time, so it's the Euclidean action is still not positive. Okay, you have.
Let me just start with the action with just one of the xi's. So those were decoupled. Let me just talk about the positive signage. Okay, we do have to continue that, but yeah, we just. So our action from now on is 1 by 4 pi alpha prime 2 pi alpha prime dz dz bar dz x dz bar x. Okay, x in an abstract field. We're just looking at this one with this sign. Okay, yeah, we would have to do that continuation and maybe with time and we do that. Okay, so this manipulation here, the fact that the integral of a total derivative is 0. Now we can use it to get some information. So, this total derivative here acts on either this action or the insertions. Okay? Now, what do we get when we act on the action? On the action we get it, so we get, I'm just opening this out. So that's e to the power minus st of x. Then I will get minus del s by delta s by delta x of sigma times O1 sigma 1 On sigma n. This is one term. And then the other terms will be plus, so this e to the power minus se acts on everything. And plus when you act on this. So plus delta x of sigma 1 by delta x of sigma, sorry, O of sigma 1 times delta x of sigma, O2, On, and so on, n such terms, where the derivative acts on each of these insertions. Okay? That is equal to 0 is a statement about the equations of, about correlation functions. So what you've done is derive an equation that relates a bunch of correlation functions to each other. This is the statement of the equation of motion in quantum field theory. Okay? Some relationship between correlators of. Now this looks very abstract. Let's apply it to a specific example. Okay? So let's apply it to a specific example. So let us start with our action and apply it to the example dz dx delta by delta x of sigma on e to the power minus s of x is equal to 0. So having no insertions. Okay? So suppose I have no insertions at all in this action. Okay? Then what do I get? I only get what I get by varying this action. Yeah? So what do I get by varying the action with respect to field? It's the equation of motion. Okay? So after some signs, which, okay, we might as well keep track of since we need in the next exercise, we will get plus 1 by 2 pi alpha prime Oh yeah, this is already difficult calculus variation. Yeah. It's probably best to do the variation in d sigma 1, d sigma 2 language. Because there the delta function is simple. So the variation will give you 1 by 4 pi alpha prime into minus del squared of x of sigma 1. You understand what I've done? Okay. I've just taken the action which is 1 by 4 pi alpha prime del x del alpha x gone back to normal notation and varied. The variation is 1 by 4 pi alpha prime into delta x with a minus sign del squared x after the integration by parts. Okay, so the coefficient of this delta x was del squared x with a minus 1 by 4 pi alpha prime. And that's what I got here. Okay, now that I've got this, I can later rewrite this in terms of del z bar. Okay, using our formula, just to make sure we get the factors of 2 right. Okay, but anyway, in this case, we just got that this was equal to 0. What we've seen is that, yes?
Shouldn't it be del z bar?
Now this is, this will be del z bar with the right factor.
Yeah, equation of motion.
Del square is del z bar, but with the right factor. So, in this case, of course, you're right, it's proportional to del z bar. But that's, okay. Del square is del z. No. So what have we discovered? We discovered that the one-point function of x inserted within the path integral obeys its equation of motion. Okay? So, that if you've just got one insertion of x, del z bar of x of z bar is equal to 0. Is this clear? Okay? Notice that I can freely take del squares outside the expectation value. Okay? Because what does the expectation value of a derivative mean? It means expectation value of x of sigma 1 minus it means expectation value of x of sigma minus x of sigma minus delta sigma by delta sigma. So that is the same thing as expectation value of x minus expectation value of x times delta sigma divided by delta sigma, which is the same thing as the derivative of the expectation values. So there's no issue about taking derivatives outside path integrals. Okay? So del z bar of x of z bar is equal to 0. So the one-point function obeys the equation of motion. Now this is going to be a pretty trivial statement because in most cases the one-point function will vanish. So it doesn't have much information. But now let's get the equation for the two-point function, which is more interesting. Let's do the same manipulation now, but do dx del by del x of sigma e to the power minus s of x with x of sigma 1. Well, let's call this sigma 1 and call this sigma 2. This is equal to 0. Now what do we get? Now we get expectation value of 1 by 4 pi alpha prime to the minus del square x of sigma 1. That came from hitting this. But there's also a x of sigma 2 sitting out. Okay? Plus, and what do we get when we hit this? Delta of sigma 1 minus sigma 2 is equal to 0. Is this clear? Therefore, because we're allowed to take these del squares out of the path integral, we get a differential equation for the 2-point function of x with x. The differential equation is simply the del squared by 4 pi alpha prime. Okay? Let's say del 1 squared because that's in this guy. X of sigma 1, x of sigma 2 is equal to delta of sigma 1. No, I think not.
No,
What's wrong with that? No. Oh, but wait. I may have messed up on factor of 2. Because when we varied, we should have got a factor of 2. Okay? So this is 2 pi. So 2 terms to it. Great. Okay. Now, this equation is enough to completely solve for this Euclidean 2-point function. Because clearly from translational invariance, this thing is only a function of sigma 1 minus sigma 2. Moreover, from rotational invariance, it's only a function of mod of sigma 1 minus sigma 2. Okay? So, let's move sigma 2 to the origin. Let's call the mod of sigma 2 r. Okay? So this is del squared by 2 pi alpha prime on some function of r. We have to figure out what that is equal to delta of r minus 0. Delta 2 of r. Okay. Now all of you know the solution to these things, but let's work it out anyway just so that we get the factors right. Okay? So what we want is a solution to del square equals 0 everywhere except the origin. And we want its flux to be 2 pi alpha. Okay? Now you know how to solve that, right? You think of this del square as del dot del f. Okay? So if, and think of this as sort of like an electric field. Del f is like E. Okay? Now, you know that the flux, this del squared, what I'm telling you is that you know that the answer is going to be a log. All of you know that the answer is going to be a log. And the way that, so we know that f of r is going to be some a times log r. Okay? You can easily verify that a times log r obeys del square equals 0 away from the origin. Because yeah, why does it obey del square equals 0 away from the origin? Because away from the origin you've got non-singular, I mean everything's non-singular and the formula for del is 1 by r d by dr r d by dr. By d by dr on log you get 1 by r cancel, and d by dr of constant, so you get 0. Okay? But at the origin, log r is not killed by del square. And the extent to which it's not killed, you can judge by computing the flux of its gradient. So what's the gradient? The gradient is a by r hat. Integrated around the circle. So you get a by r 2 pi r. So log r has flux 2 pi a. We wanted flux 2 pi alpha prime. Okay? And so we get the equation that f of r is equal to alpha prime log r, which is equal to alpha prime by 2 log of z bar. Z bar is r square. Okay? So I'm claiming that x, by solving this so-called Schwinger-Dyson equation, we concluded that x of sigma 1, x of sigma 2, okay, let's say z1, z2 is equal to alpha prime by 2 log of z1 minus z2 Z1 bar minus Z2 bar. Okay, now it's truth time have we got factors. Correct. Oh my god, minus. Okay, I messed up on a minus. The answer is, the 2 is right, but the minus is wrong. Well, let's try to try that. Okay. Wait, e to the power, we had e to the power minus s, so there was a minus from there. Then there was a minus from the integration by parts. Yeah, I got the equation. Okay. So the variation of this part actually came with a plus. There were 2 minuses. You see, there was a minus because we had e to the power minus s, and then another minus because we had an integration by parts with the reaction. Okay, good. So this was the equation. Okay, and then everything else goes through except that we put minus. Okay, that was painless. Yes.
Die of it like larger.
Shouldn't it die off at larger? This is a good point, but it doesn't. In 2 dimensions, every higher dimension, the Green's function of del square dies off at larger. In 2 dimensions, it doesn't. This will make, actually, this will be the reason that x itself will not turn out to be a good operator in this theory, because its insertions are not sufficiently localized. Okay, but things built out of x will turn out to be. So a very good question, but hang on. It does not turn out. It's just a fact. Okay, it's a fact that in 2 dimensions, if you put a 2-dimensional electromagnetism, you put a point charge, its potentially is logarithmic. Yes.
This is one function of 2 scalar fields in 2D CFT.
This is a 2-point function of 2 scalar fields in this free 2D CFT.
This is a normally defined one function, derived one function in 2D CFT.
You can derive it in any number of ways. You know, if you open Peskin-Schroeder, they will derive it by, how will they derive it? We're going to momentum space and doing an integral. Okay, often you derive it this way. Find the Green. This is a Green's function. This is the equation for a Green's function. Yeah, often people will derive it this way. You find the equation on a Green's function and solve that equation. But there are many ways to derive it. One of it would be to go to momentum space. Why don't you try this as an exercise? Derive it using Feynman diagrams in momentum space. Okay? It's in momentum space clearly it's 1 by k square, right? Now what you have to do is Fourier transform 1 by k square. Okay? If you Fourier transform 1 by k square, tell me by dimensional analysis what you can get. It has dimension 0 because we did k by k square. What else can you get by the log? Okay? You'll have to do it a bit carefully to see you get exactly these factors. That would be another way to do it. I do it this way just because we will be using path integral manipulations as our bread and butter for the next 10 lectures or so. So I'm trying to get you used to using these path integral manipulations even to derive things that you already know and love. Just so that you won't be too suspicious of these derivations once you get to things that you don't know but also love. Okay. Other questions or comments?
Probably asked, you said this before, but what length scale are you actually going?
What length scale? Have I said? Oh, you mean H bar? Is that what you're doing?
The length scale, because you have log R, right?
Ah, what length scale have I said to? No, I haven't said it before. You see, what this is telling you, what this is telling you, you see, to this thing we could always add a constant. Okay? So I could put any length scale you want here. Let me call this length scale A square. That will not change the fact that we base your differential equation. And this A square will essentially be our cutoff. But when we renormalize the theory, we will remove it. Okay? So we will work in a regulation scale. Okay. Now, what I'm going to try to do is to introduce another path integral manipulation I'm going to try to introduce another path integral manipulation for you. So we learned how to deal with the equations of motion in quantum field theory, and as an example, we use that equation of motion to derive the two-point function of the free scalar. There's another path integral manipulation that is very important that we will use continuously through our course, and that's the path integral manipulation that allows you to derive no-free charges. Okay, so I'm going to introduce the path integral manipulation that allows you to understand the Noether procedure in a quantum setting. Okay, so suppose we've got some dx e to the power minus s of x, completely abstract, and this action has a symmetry. What does that mean? What does a symmetry mean? A symmetry, from the point of view of the path integral, is a change of variables. X is equal to x prime. I'm going to talk about continuous infinitesimal symmetry. So x prime plus epsilon times delta x, delta some function. Okay? Epsilon is small parameter. So that when you plug this variable change into the action, the product of measure and e to the power minus s remains invariant. Meaning that if you just do the change of variables here, this will turn out to be dx prime e to the power minus s of x. If you can find such a change of variables, such that under this change of variables, you plug into the integral and you find that this remains, you get the same thing back. That is called a symmetry in quantum field theory. Okay, so this is our definition of a symmetry. It's a clear definition in terms of path integrals. Usually the symmetry will independently leave the measure and the action invariant, but not always. All we need is the product of the two be left.
But won't this change always leave as in that integration measure is the integral over all functional forms of x?
So it will always leave the answer invariant. But that's not what that was not our definition. Our definition is that it should leave this form invariant. That you will always be able to write in this form times some function of x. That this function is the same as this defines a symmetry. You understand? There are two separate questions. There's the question of what is the answer to an integral and what is the form of the integral. Let me give you an example. Okay, let me give you an example. Suppose I was doing an integral over two-dimensional polar coordinates. Okay? And I had a function that was just a function of radius. I have r, dr, dθ. Okay? I want to know, using a definition similar in spirit to this, what are the symmetries of this integral? Now, an integral is an integral. In any integral, you can change variables. Okay? Nobody can stop you. So to get the answer, you can do whatever you want. But that's not my definition of symmetry. My definition of symmetry is that it takes the same form within the integral. So let's look at an example of something that is a symmetry. If you take theta goes to theta plus delta theta, that's a symmetry because theta goes to theta prime plus epsilon is constant. That's an example of symmetry because this is equally written as r dr d, and r is equal to r prime. R prime dr prime d theta prime f of r prime. Now, what is not an example of symmetry? Something that's not an example of symmetry is r goes to r plus epsilon times, well, even r or r squared, let's say. Okay? Because under this change of variables, firstly you will get change from the measure, but secondly you will change f. You see, we will have f of r prime plus epsilon r prime square. When you Taylor expand this is f of r prime, which is what you wanted, but plus an additional term that you didn't want, which is epsilon times f prime of r prime times r prime square. So though the integral will remain the same as a number, its its form expressed in terms of your variables has changed. That is not a symmetry. Is this clear? Okay, so symmetry is a change of variables of the path integral under which the path integral retains its functional form in terms of the new variables. The same functional form that it had in terms of the old variable. Is this clear?
Yeah.
It's a confusing point.
Initially, when we talked about symmetries, we always talked about symmetry with the action. Right? No, we didn't care about what the path integral looked like. So that was a classical way.
That was a classical thing because in classical physics, all you have is the action. Now, as I say, most often our symmetries will be symmetries both of the measure and of the action. So it will be the same. Sometimes you can have more mixing. Sometimes it won't even be sensible to, depending on your regulation scheme, you can take from one to the other.
So this analysis of something that keeps the classical action invariant but changes the measure is enough to say that the symmetry is not preserved as a quantum variable.
It's enough to say provided you cannot modify things to get rid of it. This is the question of anomalies.
Yeah.
Okay? Not every variation cannot be got rid of. Those that cannot be got rid of by adding a local counter term are genuine anomalies. If you have a variation of the action under action plus measure under symmetry, but you can change the action by a local counter term to cancel the variation, then the original action was anomalous, but it was a trivial anomaly because you could change the definition of your theory a little bit to get rid of the anomaly. We normally say that a quantum field theory is an anomaly if the variation of action plus measure is such that, under symmetry, such that it cannot be cancelled by the addition of any local.
But how would that make the measure invariant?
Well, you just have to make the whole thing invariant. You don't need to make the measure.
I mean, you add counter terms only to the action, right?
Yeah. So that's the point. The point is you have a symmetry as long as the measure plus action is invariant. So if you get a variation from the measure, which you can cancel by a variation from the action, yeah. Okay, because all we care about is the path integral.
Okay.
What came from the measure, what came from the action, often that's in your beholder's eyes, actually. Yeah. Okay, great. Anandita, is this clear?
So my point was the measure is like over all functions of x, like that capital D.
X of sigma is anything, yes.
Yes. So won't dx prime be always the same as dx?
No, there's a Jacobian fact. It's true, its range is the same, but there can be a Jacobian, right? So suppose I take r goes to r squared. Dr goes to r dr. The range in both cases 0 to infinity, let's say. But the detailed measure is different. Okay? Other questions or comments? Okay, excellent. So now we know what we mean in terms of for a path integral to have a symmetry. Okay. Now I'm going to derive consequences of a path integral having a symmetry for the observables of quantum field theory, namely operator insertions. These consequences have a name, they're called Ward identities. Okay? But we're going to derive these purely from the path integral, which may differ from other derivations that you may have seen. Okay? This is often the best way to think. You keep the factors straight. Basic. How do we proceed? What we do now is to say, suppose this was a symmetry of the path integral. But I now make epsilon a function of x, this is sigma. Given the symmetry, I perform a second change of variables. One in which the parameter of the symmetry is replaced by a function of sigma. Okay? Now what happens to the path integral? Okay. Now what happens to the path integral? We're really interested in the path integral along with integration, along with insertions. So suppose I had the path integral dx e to the power minus s of x O1 of sigma 1 On of sigma n. On this path integral, I make this change of variables. What do I get? Well, this part would have been invariant had epsilon not been a function of x. Therefore, its variation, its change, okay, must be something that depends on derivatives of epsilon. Because were all derivatives to vanish, it should vanish. Therefore, the change, suppose we call this z, it should be that delta z, the contribution of delta z from this part is equal to dx. Okay, instead of delta z, let me put z prime is equal to, the new z after I make the sheet derivative. It's equal to dx prime e to the power minus s of x prime plus integral del mu epsilon j mu for some vector g. We have to times O1 to On, and we have to include the terms because of the change of variables acting on these. We'll do that in a moment. But first I'm just looking at the action of the change of variable of this. Now, some of you are wondering what the hell is going on, yeah? One thing you might wonder is, why do you have only one derivative? Why not 5 derivatives? It's fine if we have 5 derivatives. If we have 5 derivatives, we have a 5 index object. We'll transfer the derivatives by integration by parts to the other object. Okay? If you have more than one derivative, we don't care. You can always write it in this. The point is that there's no terms with 0 derivatives. Some of you are wondering, why does this go with the exponent? Why not downstairs? And the answer is very easy, with the infinitesimals. So whether we put in the exponent or downstairs is a matter of aesthetics. And it's aesthetically more pleasing to put it in the exponent. Okay? And then, are any of you wondering anything else? Okay. And then what we have to do is to evaluate what we get from the remaining changes. Okay? So we will get plus integral dx prime e to the power minus s of x prime. Then delta O1, O2, O1. What is delta O1? Remember, O1 was a function of x. Whatever the function of x is, we do the change of variables in that. It becomes the same function of x prime plus a small change. You understand? So it's obvious what it is. Plus we get the term O1 delta O2, and so on. Is this clear? Okay? Is this clear? Any questions or comments? Okay. Now, let's rewrite this equation. Now we can be less aesthetic and bring this down. Okay, now there's an important point. This is z, this is z prime. But what can we say about the numerical value of z as compared to z prime? It's the same, because we've just taken an integral and expressed it in different variables. So this is equal to this. Now there's no difference between x prime and x. We're under the integration sign because they're double variables. We're doing an integral. So once we've written it out, we can just replace x prime by x. Okay? Expand this exponential. The term which is 1 will cancel this. The term which is epsilon mu j mu will not cancel it. Okay? And so we get the equation. And so we get the equation. Integral del mu epsilon j mu. Okay, integral del mu epsilon j mu O1 On plus delta O1 O2 On plus O1 delta O2 On and so on. O1 delta On is equal to 0. Okay? Now, this is under the integral sign. This is under the integral sign, so we can rewrite it by integrating by parts and putting the del mu here. We'll choose our epsilon, which is a function which is in our hands, so that is where it dies off fast enough at infinity, so it justifies the integration by parts.
Sign
We get a
is-
minus sign, yes. Okay, now let's take various special cases. Let us suppose that we choose our epsilon to be, we've got various operator insertions at points sigma 1, sigma 2, sigma 3 up to sigma. They're distinct points. Let us choose our epsilon to be some function that has non-zero support only to the exterior of sigma 1, sigma 2, sigma 3.
Sorry, now all these delta ones and all will be proportional to
Epsilon.
right?
Yes, will be proportional to
X
epsilon.
of epsilon.
Yes, but hang on to 2 minutes. Yeah, because it's proportional to epsilon of x. So hang on, it's a bit wrong. It's not a constant.
So the minus sign is from?
What?
Minus sign is from?
By parts. Integration by. I have del mu epsilon.
I see.
Okay?
What if sigma 1 and sigma were cut off length apart?
Sigma 1 is yeah. So now sigma is the one the insertion point here.
Yeah.
Well, yeah, because I can choose. We're going to look at all cases. But since epsilon is in my hands, I'm going to take the case first where it's well separated from everything else. Okay, let's first look at that case. In that case, all of these are 0. Because epsilon is 0 where you have the operator insertions, and the operator insertions are local functions of x. Okay?
Del mu epsilon is O1 O1.
No, that will actually change. Because this was integral over sigma. It's completely independent of sigma 1, sigma 2, sigma n.
Oh, see.
Okay? Fine. So let us first take the case where these guys are well separated. Then we get everything else is equal to 0. And so provided your insertion point, your current, okay, provided your current insertion point is separated from all the other insertion points, then we get the equation del mu de mu O1 sigma 1 On sigma n is equal to 0. Okay, under the condition sigma not equal to sigma 1, not equal to sigma 2. You know what I mean? And sigma doesn't coincide with anything. That's clear? You see, this was our equation.
Yes.
Now, delta O of 1 was the change in the insertion because of our change in variables.
Yeah.
Now, our change in variables was x mu is equal to x prime mu plus epsilon of sigma times some f of x. Suppose I choose a point sigma that is separated from all of these others, and I choose my epsilon to be non-zero, only away from all of this. Then there's no change there. There's no change in variables for the path integral for those guys. Okay, so all the delta vanish. Okay, is this clear? Okay. I need to move. On the other hand, now we will look at what Mangesh was saying. Mangesh was saying that, look, yeah, now suppose we take the case where these O's were some ultra-local insertions. O1 depends only on X at sigma 1. Okay? So now we go back to this equation. So you get what we've got is the equation integral epsilon of sigma d mu on j of sigma O1 sigma 1 On sigma n. Okay. So in the case of these alpha locals, this delta O n is equal to epsilon m. So epsilon of sigma m times some delta. I should give some delta tilde O. This is clear, right? It's a first order change. So it's proportional to epsilon at sigma m. Okay? So what we will get is this is equal to O1 sigma delta O1 sigma 1 times epsilon sigma 1 On sigma n plus n such terms delta tilde. I've just written it, just rewrite. But look at this. This is an integral over all sigma. It's picking out only epsilons at particular sigmas. What can that tell us about this function? This tells us that this function, this tells us that del mu of j mu of sigma O1 sigma 1 On sigma n, okay, is equal to delta of sigma 1 minus sigma minus sigma 1 delta tilde O1 of sigma 1 On plus delta of sigma minus sigma 2 O1 delta tilde O2 of sigma 2 On plus all these. Is this clear? This is now a relation for correlation functions involving the current and other operators. It is the generalization to the path integral of the statement that in classical physics del mu j mu is 0. Del mu j mu within the path integral is 0 provided j is not inserted coincident with any of the insertion points. If it is inserted coincident to some of the insertion points, you don't get 0 within the path integral, you get these delta functions. Okay, this is the statement of the Ward identity associated with a symmetry for within the path integrals. What I've said now is just generally true in quantum field theory. Doesn't use 2 dimensions, doesn't use conformal invariance. It's a general statement, though it will be particularly useful in 2 dimensional conformal field theory, as we will immediately see. I'll take 5-10 minutes extra. Okay, any questions or comments about this? Okay, this business about things coming near is these delta functions.
I'm worried about cutoff lengths as opposed to 0.
Oh, you're worried about cutoff lengths as opposed to 0. Okay. Well, suppose you have to be really specific with it. So suppose you got a lattice. Okay? Then this delta function would just be replaced by Kronecker delta. Okay, with the right measure. Okay. If you had some other regulator, you'd have to look at it carefully. You probably get a smear delta function. Okay? But in any particular case, you'll work out what you want.
Okay.
Is this clear? Okay? In fact, in a lattice, the derivation will be very clear. Because it's just that particular variable. Okay? Now, okay, I won't confuse you about this. I won't confuse you. Yeah, fine. Unless it's a question about it, I won't confuse you about a slightly confusing point. And okay, so this is a nice word. As I said, this was just very general. But in our study of two-dimensional conformal field theory, again, in our study of two-dimensional conformal field theory, we will often encounter the case. Okay, we will often encounter the case when our conserved currents. So notice, for instance, that when we are away from other insertion points, as we've seen, del mu J mu is equal to 0. And this is a precise statement. I want you to remember exactly what the statement means. It is a precise statement about a function. What is the function? The function is a function of m plus 1 variables. The insertion point of J and the insertion point of the other operators. As a function of these variables, this function is analytic. I'm sorry, it's conserved. It should be analytic. It is conserved. You know, so this correlation function, the function of sigma 1, sigma 1, blah, 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 that function obeys this equation. Del mu sigma on that thing is equal to 0, unless possibly at points where sigma hits the other points. Okay? So it's not some blah 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 statement about, I mean, it is, of course, in a deep level, it's a statement about some operator. But we've converted it by looking at the path integral into a concrete statement about functions. Okay, so what it means is very clear. It's a statement about functions. Now, del mu J mu equals 0, there are many possible ways in which that would work. But as we will see very soon, in the case of two-dimensional conformal field theory, we will encounter many currents that are conserved in the following interesting way. See, del mu J mu in complex coordinates is proportional to del z jz bar plus del z bar jz. Why is it z and z bar? Because the metric has only off-diagonal terms. So if you raise this is del z jz, but if you lower both indices, del z jz bar. Okay? Now, one way you could have a current like this conserved, one way in which a current like this could be conserved, is if jz bar was jz bar of z bar. And jz was jz of z. I emphasize that this is a statement about correlation functions. Insertions of jz are analytic functions of z, apart possibly from where z hits other insertion points. Suppose that were true, then that would ensure that the current was conserved everywhere except for insertion points. Okay? And we will see that this is often the case for many of the, basically always the case for all the conserved currents we will be interested in. Okay? So let me assume this is the case for a moment. Okay? Let me assume that this is the case for a moment. Okay? Let me assume this is the case for a moment and proceed. Okay? Let me assume this is the case for a moment and proceed to try to find consequences. To try to find consequences. To try to find consequences of this word identity that are specific to the case of a two-dimensional conformal. Okay. Now the first thing is this. Suppose we have this statement, then we can take this statement and integrate it over a region. Okay? So we can take the statement and integrate it over a region. Because this guy is a total derivative. I'm integrating it over sigma. Because this guy is a total derivative, this becomes a boundary term. Okay? And because we integrate over we integrate over a region, we just get clicks from the delta function for those points that happen to lie within that region. Okay? So suppose I've got some insertions such as sigma 1. Let me take the particular case that only one of the insertion points lies within a region. Generalizing to the case where many of the insertion points lie within the region is trivial. Okay? So, suppose only one point lies within a region. One of these insertion points, all the other points are sigma 2, sigma n are outside. And I take this equation and I integrate it. Okay? Now, what do I get? I get that this is the normal component of J. You know, I'm using whatever, Gauss, whatever, that theorem. That's the normal part of J integrated on the surface. Okay? Now I'm going to do this normal part of J. I want to write this in terms of Z and Z bar components. This is a bit tricky, so let's do it. So, suppose we've got a little region here. Okay, and this little region is parameterized by, in this little region we've got a dx and a dy. You know, this little region, you move a little bit in the x direction, a little bit in the y direction. Okay. Now, I want to know what component of J lies normal to this region. Clearly, the normal direction to this little vector, which is dx dy, is the vector minus dy dx. You know, that's the normal direction. Okay? Now, I will want normal times length. Okay? So if I just take this guy, which has the same length as this guy, both are dx squared plus dy squared, and dot with j, I'll be getting j dot n integration over length. Okay? So the thing that I want to compute here is jx minus jx dy plus jy dx integrated over my surface, over my little boundary surface. And now I want to take this object and rewrite it in terms of analytic and anti-analytic stuff. Okay? I want to take this object and rewrite it in terms of analytic and anti-analytic stuff. So let's do that. Okay, so let's do that. It's a bit of a, okay, there are many ways of doing it, but let's just do it brute force, just to make sure we do the numbers that's right. Okay, so Jx is equal to Jz. Oh God. This is lower than this is, right? I'm sorry. Okay, let's just do it. Jx is equal to Jx goes like del x. So del x went like what? dz by dx. So that was 1 times del z. So, del z plus del z bar. Del y would be equal to del z I times del z minus del z bar. Right, because dz by dx was 1 and dz by dy was I. dz bar by dx was 1 and dz bar by dx dy was minus 1.
Sir, isn't that a byte?
What?
Byte.
No, I don't think so. Because you see, we had z is equal to x plus I1. And the chain rule we're using is d by dx is equal to dz by dx d by dz. In this way of differentiating, there's no end.
It is there when we transform dx.
Exactly. So it's the upper versus lower. So that's why I worked out the derivative so we can get this guy. Okay. So This guy is minus of dz plus dz bar into dy. Dy is what? Dz minus dz bar by I. By 2i. Yeah. Okay. Plus jy, which was I times dz minus dz bar sorry, j also jz minus jz bar into dx, which is dz plus dz bar by 2. Okay, and now we have to collect terms, and if we've done things right, we get a nice answer. Okay, so let's see. Yeah. Yeah. So we get jz dz. Basically, we get jz. Okay, let's work it out. We get jz. See, the jz dz term is minus. Okay, so this is minus. Let's put this I up here and make it a plus. Okay, it's I jz dz by 2, and here we get I jz dz by 2. Okay, so we get jz dz, and jz bar dz bar is I jz bar minus I jz bar dz bar by 2 minus I jz bar dz bar by 2. Okay, minus jz bar dz bar. Okay, and if you stare carefully, what? Overall, I by 2. No, not by 2, but the by 2 because there are 2 terms. So overall, I. Okay, and now you stare carefully at the jz dz bar term. So that's I jz minus dz bar, I jz plus dz bar. So those cancel. So this whole normal derivative of j on the surface is the integral jz dz minus jz bar dz. Okay? So now we see something quite amazing. The amazing thing that we see is that if we're in the situation, okay, if we're in the situation where jz is a function only of z, and jz bar is a function only of z bar, this integral has reduced to 2 contour integrals of analytic functions. Okay? So it suddenly becomes clear that all the beautiful techniques of complex analysis, okay, all the beautiful techniques of complex analysis will play an important role in our study of two-dimensional conformal field theory. In particular, the study of what happens when we do analytic contour integrals of analytic functions. Okay, so what do we get? We get integral jz dz with an I minus jz bar dz bar with an I. Okay, let me ignore the jz bar dz bar term. Okay, it's just repeating everything I'm going to say. I'll pretend the jz bar dz bar term wasn't there, and then we deal with words later. So let me write down the formula so that we become more tractable. On I jz dz of O1 of sigma. Okay, O1 is understood to be at point sigma. On, okay, is equal to delta O1, O2, On plus O1 delta O2 On and so on. What else do we know? You see, what else do we know about this J? We know that this J function here is analytic. Okay? It's analytic except possibly at insertion points. What kind of analytic function, except at insertion points, will have the following answer to this contour integral? Exactly. A function that is analytic up to poles. Okay, a function that's analytic up to poles and such that the strength of the poles are delta O1, delta O2 and so on. So, we conclude that we've got Jz O1 okay, irrespective of what's happening with the other guys, the singularity that occurs when J approaches the insertion of O is equal to delta O1 by Z minus Z. There could be worse singularities. There could be 1 over Z1, Z minus Z1 square singularities that we don't know anything about. So let's put a dot. And there could be lots of regular terms that we don't know anything about. Delta O1 by Z minus Z1 plus dot. That we don't know anything about. But we know that when J hits O, there is at least a pole singularity, and the strength of the pole singularity is delta. No, actually I'm lying, because there's the other term as well. There's the anti, there's the JZ bar. So what we really know is that the sum of the strengths of the singularities, when J hits O and J bar hits O, is delta O. But as you will see, in many cases we will deal with currents which have only an analytic part or only an anti-analytic part. You'll see that as we proceed. In which case we completely know, since the anti-analytic part is just 0, Jz is the only current in town, and then this is literally true.
So, why are you calling it anti-analytic?
What?
Why are you calling it anti-analytic?
Anti-analytic is something that was a function of Z bar. I don't know if that's standard terminology. Anti-bar. Fine. Okay. So, this ward identity, which is a general feature of quantum field theory, has turned into a statement of complex analysis. Has turned into the statement that the operator product expansion, and if you don't know what that is, we will define it and derive its properties in the next class. Okay? That the operator product expansion has a singularity. Between the current and the operator has a singularity. And we don't know anything about the earlier singularities, but it must have a pole. And we know the strength of the pole. Okay? So, the Ward identities in two-dimensional conformal field theories. Okay, you can ask, where do I use conformal invariance here? Nowhere, except that I asserted that Jz was an analytic function. Usually that's not the case with our conformal invariance. Whereas in conformal field theories, we will often have the situation where Jz. So, in two-dimensional theories where Jz is an analytic function and Jz bar is an anti-analytic function, which is usually only true in conformal field theories. Okay. We've converted the statement of the Ward identities into statements about poles in the OPs of statements about poles in correlation functions between J's and insertion points or other operators. Okay, this is a clear statement about functions. What are the functions? They are correlation functions. Notice that this clear statement actually did not depend on what other operators you inserted. It did not depend on how many other operators were inserted inside your circle. It did not depend on how many other operators are outside your circle. It's a local statement. So it's a statement not about just one function. It's a universal statement about all correlation functions. J and O, no matter what other insertions, there is a pole in this. With the same strength. This is a small illustration of what is called the operator product expansion that we will discuss in the next class. Okay. Questions or comments?
This current J corresponds to the conformal symmetries, or it can be other symmetries?
Could be any symmetry that is analytic. For instance, in a conformal field theory with the Cauchy-Moody algebra, you have many other analytic currents which have nothing to do with conformal symmetries. Right? And this property holds. Any analytic current. Okay? We will most use it in our course, in the first part of our course, for conformal currents. But it's much more.
But the two-point functions, like in the conformal field theories, say the JJ two-point function will have this 1 over z minus z bar type of z minus z1 type of behavior. So is it tightly linked with this? I mean, if you use conformal invariance, then you can fix the two-point function of the j's. So the first term in the OP.
You're asking what about the case where O's were other J's? Okay. Suppose you've got a non-abelian symmetry. If you've got an abelian symmetry, then that tells you that J with J has no pole. Because it's a defining property of an abelian symmetry that the current itself is invariant under the symmetry. Okay? If this is invariant, there will be no pole. As you know, there will instead be 1 over z minus z1 square situation, which is the level of the Cauchy-Moody algebra. But as not everyone here knows it, we won't talk about that for a moment. On the other hand, suppose you have a non-abelian symmetry. Then, one current transforms another. And then you will have something like this, where the coefficients here will be the structure constants. Okay? So, in a particular example of this will be JA, JB of Z1, Z2 will be equal to FA, ABC, JC over Z1 minus Z2. Because that's how the transformation, the Ath transformation acts on the Bth current. And that's what the case will be when we study non-abelian Cauchy-Moody algebras. But hang on, things will be simpler for a while before we get to such complicated. Any other questions or comments?
All this analysis is worked out when you assume that G was actually monomorphic or
yes. But if it's not, all bets are off. Yeah, none of this, none of this. The first part, this is true.
Yes.
Translating this to this requires holomorphicity.
Yes.
So we will be careful to use it only in cases where we can check that the currents are holomorphic. Okay?
So that's a separate case.
It's a separate exercise. Okay, but let me quote a theorem, which we will prove in one of the lectures. Theorem: any unitary conformal field theory with a dimension first, just a little terminology. Explain why. Maybe I should introduce that. I've been introduced as terminology properly, but in a conformal field theory, in any quantum field theory, you can talk about any conformal field theory, we can talk about dimensions of operators. In two-dimensional conformal field theories, you can talk about the left and right dimensions. Okay, which is basically dimensions under dimension plus spin and dimension minus spin. It's basically that. We will do this systematically. Okay? Let me just tell you. Now, just from symmetric properties, it follows that Jz has left dimension 1 and right dimension 0. Jz bar has left dimension 0 and right dimension 0. Okay? Theorem, which we'll prove. Okay, lecture 2. Any unitary conformal field theory with a mass gap. By mass gap, I mean if you take the theory, put it on a circle. Then there's a unique vacuum state and then a gap. Okay, any conformal field theory with a mass gap. Okay, a dimension 1-0 operator must be monomorphic. Okay, we prove this. So it's more than a coincidence that holomorphic currents will show up all the time in the study of conformal field theory. So almost a theorem. Now, why is it almost a theorem? I said this was a theorem. It's almost a theorem because I said any conformal field theory with a mass gap. Now, perhaps the theory of interest will not have mass gap. What about the free bosons? Does it have a mass gap? No. It has a mass gap for oscillators. Oscillators has frequency 1 and 2. But what about zero mode motion? Zero mode was like, what are the states of the zero mode sector? Do you remember what we did last time? The zero mode sector was like the quantum mechanics of a massive particle of mass 1 over alpha, right? What is the lowest, what is the spectrum of energies for such a thing? It's k square, right? K square times m by m. It's k square. K square starts at 0. The k is 0. So our free boson theory does not have a mass gap. Okay? So this is a very good example of the use of theorems in physics. You can use excellent theorems which have nothing to do, can have nothing to do with physics. Okay? So it tells you that you should expect this a lot. It won't always be true. For instance, in our theory, we will have there's symmetry to do with rotations. Rotations in space-time. You can ask, is the current for that holomorphic? Answer turns out to be no. And it's this mass gap, lack of mass gap that spoils the theory that it shows the gap. So not every current in this theory, in the theory of interest, will really turn out to be holomorphic or anti-holomorphic, but most of them will be. Because there was an almost there. You see, a theorem with assumptions. Okay. Other questions?
What do you mean by conformal field theory from mass gap?
You see, it was a mass gap once we put it on a circle. Let me say that again. A conformal field theory on R has no mass gap, has no length gap. But a conformal field theory on a circle, okay, has a spectrum of states that could consistently be 0, 1 by R, 2 by R, 3 by R. But it could also consistently be 0 and then alpha by R, where alpha is a continuous number that ranges from 0 to 3. None of this violates, neither possibility violates conformality. Is this clear? Okay? No conformality theory can have a mass gap when studied on R, because there's no length gap. But conformal theories can and often will have mass gaps when studied on a circle. Okay? As you will see when we study the state operator map in our next class, you will see that the mass gap of the theory on a circle translates to a mass gap in the spectrum of operators as a function of dimension. So we'll turn into the question of whether the spectrum of operators, whether you've got a continuum in the spectrum of operators with all dimensions, or the spectrum of operators as a mass gap. You will see that this way. Hang on, we're in the early days here. Other questions?
Yeah, if O's are not functions of x but some differential functions of x,
Good.
then actually you will have all these statements with epsilons hanging around it. So is it like an infinite class of?
Okay, this is the complication this is exactly the complication I said I would not worry you with when you ask a question, but since you've asked a question. If you've got differential functions of x, the way we will think of this is that every differential function is a derivative, is something minus something else. So in the end, what you will get is derivatives of epsilon. Okay? And then you will get, so you will get basically derivatives of delta functions. Hanging out here. Okay? And this derivative of delta function, you think of as delta function minus delta function. So you may then make predictions of higher singularities. So you can trace it through, basically. Okay? We will do examples of these as we go along. Hang on for a lecture, because it's an excellent question. It's a question somebody should have asked. Okay, other questions? Okay, fine. So in the next class we will discuss an example of this Noether current in conformal field theories in general. You know, the current that we will discuss is the stress energy. Okay. We will then discuss more general properties of two-dimensional conformal field theories, the operator product expansion, the state operator map, and then we will return to solving our theory and computing all its correlation functions directly in Euclidean space, our free boson theory, study a few other theories, and then we will, maybe 2 lectures, return to the study of string theory as opposed to conformal field theory. But well armed with these techniques. Okay, thank you. Sorry.
I don't know.